Okay, so intro to specific heat capacity part 2. Sorry, I was struggling in the last video, but here we go. So what is specific heat capacity? So just like when we were looking at the copper samples versus like plastic or wood, the different types of substances will transfer energy differently. And so the specific heat capacity is what that's all about. So this is the amount of energy that it actually takes in order to raise 1 gram of a substance by 1 degree Celsius. So the amount of energy it takes to increase 1 gram of a substance by just 1 degree Celsius. 1 degree Celsius. And so there are a few different units of energy that we could use, but for specific heat capacity, the units that we use for energy are what we call joules. And we represent that with a big J. So it's joules like Joules, not joules like in the jewelry. And so for water, the specific heat capacity is 4.18 joules for every gram degree Celsius. So those are the units of specific heat. Joules per gram degree Celsius. We could also have joules per gram Kelvin. Because Celsius and Kelvin have the same sized units, we can use those interchangeably. It doesn't matter which. Just be consistent with the problem that you're working on. So that's what specific heat capacity is. So for every type of substance, it's a little bit different. So for metal, it's different than plastic. For different types of metal, it's different. For water or liquid or solid, it's different. And so whichever problem you're working on, you'll need to identify which substance it is that you're working on and which specific heat capacity you need to use. So we have an equation in order to calculate the total energy. So we could say, let's say we have a system and we're putting energy into our system. We want to know how much energy does it take in order to raise your sample by a very specific temperature. We would call this not just thermal energy, but Q. So remember that Q is the flow of thermal energy. You might see this equation written both ways though, but I'm going to use Q. So Q equals the mass of the object, so we already know that that's important from looking at our water samples, times the specific heat capacity times the change in temperature. Sorry. So you are going to see this written a little bit differently. It doesn't matter which order these 3 variables are written in because it's multiplication and it will not affect the answer. So remember that Q equals the heating or flow of thermal energy. M is the mass of your sample. C is the specific heat. Now in your book, if you look in chapter 10.2, they actually use S for specific heat, so don't let that confuse you, but we're going to use C. And then delta T is a change in temperature. So when you calculate the amount of energy it takes, all you need to do is just figure out where all your variables are and plug them into this equation. So let's go over a quick example. So you're now going to work on this worksheet. You're going to start on this side, graph the data, go through each one of these problems, and then on the back, you'll go ahead and work on the specific heat problems. But let's go through a problem together briefly. So let's just write down all of our variables first, and then just plug them into the equation. So gold has a specific heat of 0.129 joules per gram degree Celsius. So that's my C. How many joules of energy, so we're calculating the Q, are required to raise the temperature of 15 grams from 22 to 85 degrees Celsius. To calculate this delta T, you need to find the difference between these. So go final minus initial temperature. And now we just plug it in and solve for Q. So we have Q equals 15 grams, 0.129 joules per gram degree Celsius. 85 minus 22 is 63 degrees Celsius. And here I can see grams cancel out, degrees Celsius cancels out, and I'm left with the units of joules. So let's see what I get for this. So 63 times 15 times 0.129 equals 129.9. Or 121.9. I want a few sig figs in my answer. So around 120 joules. This problem is endothermic. It's going to require this much energy in order to raise the temperature. And I know that because this is a positive number. If you're very careful about subtracting final from initial here, this delta T will be positive or negative. If it's negative, then your whatever's happening here is exothermic. All right, have a good day today. Be on your best behavior and see how far you can get on Introduction to Specific Heat Capacities. I'll see you tomorrow.